Hey guys, Ego here. Today we're going to be talking about 3D line intersections. In the previous video we talked about 2D line intersections and how we could use them for raycasting. Now 3D line intersections aren't necessarily as broad a thing, they can't really be used for things like raycasting, but they do come up occasionally, so you might find use for them, so I figured we might as well talk about them because I haven't made a video in a while and this is something that I can talk about. So before we get into the digital blackboard and all that stuff, I want to kind of get out of the way a really important concept because it's very hard to draw in 3D, as I'm sure many of you are aware, so I figured it would be best to actually kind of show you ahead of time what we're looking at, even though it's kind of skipping some steps. So don't necessarily worry about how I calculated this stuff. Just worry about visualizing it, because I'm going to mention this stuff later and it's going to need to kind of be in your brain to understand what I'm talking about. So I have this blue line and this red line, and they're built up of 4 points, so point A, point B, point C, and point D. And what's going to happen is when I move one of these points, which is going to update the lines, there's actually going to be a green line showing, because right now these two are perfectly intersecting. So let's move them out of intersection, and you'll see this green line popping up. And what this green line is, and this is what I really want you to focus on here, what this green line is it's the connection between the two closest points on each line. So the closest point on the red line to the closest point on the blue line, and that's what that green line is. So the closest point on the red line is here, and the closest point on the blue line is here. And the interesting thing, or the interesting property about this green line, is that no matter where I move these points, it is always perpendicular. This green line is always perpendicular to both the blue and the red line. And so when we think about that in terms of vectors, what this means is that the green line, the direction of the green line, so the direction of the green line is perpendicular to both the direction of the red line and the direction of the blue line. So that's very important. Please keep that in mind. So it is 90 degrees to both the blue and the red line, and that is true no matter where I move the points on either line. Now what's interesting, and this is where the intersection is going to come into play, if we can calculate this green line, which we clearly can because I'm doing it, but once again we'll talk about that later, because it is this green line represents the shortest distance between two lines. If the two lines intersect, that green line should have a magnitude of 0. So that is really what we're looking for. If we can find that green line and we know its length is 0, then we know that the two lines must therefore intersect. And I know that's a very precise test, and we'll talk maybe a bit more about why you may or may not want to do a test like this in 3D, and perhaps some things that we might do to kind of make this a bit more reasonable for use in gameplay, because that's a very precise calculation, and assuming that the player is interacting with it somehow, it's very unlikely that they will be able to perfectly align two three-dimensional lines that have really no width to them. So we'll talk about that later, and talking maybe about margin of error. But for now, let's get into the digital blackboard now that we've seen this green line, and talk about how we can actually calculate it. So I'll see you guys there. Okay, so we're now in the digital blackboard here, and I've already set up a bit of stuff and done a bit of writing just because this would take really long to go over everything step by step, but we are going to definitely go over some of the math. I've just kind of sped through writing some of it, so I'll still go over it, but a lot of it is already pre-written. We're just going to be talking about what I did in terms of the algebra and stuff like that. So first off, we're setting this thing up kind of very similar to how we did the 2D line intersection setup. These are going to be two parametric representations of P0 and P1, and we'll talk about why in 1 second. But I just want to clarify here that these two lines do not actually intersect here. That is just a limitation of me only being able to draw in 2D. Rather, we're going to pretend that they don't intersect there, that there actually is some depth between them, and the two closest points are represented by this green line, just like how it was in Unity when I showed you. So what we're looking for here to find this green line is we're looking for P0 and P1. And we're going to represent P0 and P1 as two parametric equation values. So we're going to say P0, which is a vector, is going to be equal to, and we know that R is the direction between B minus A. So if we were to say A plus R, we get ourselves B. And same thing here if we were to do C plus S. So C, and I suppose these are vectors, C plus S is equal to D. And so therefore, if we were to scale R or S by some scalar values, we can get really any point along these lines. Now we know that if the scalar value is between 0 and 1, then the actual value that we are getting is actually on these line segments. Otherwise, if we get a value greater than 1 or less than 1, then we're going to have a line that goes beyond, or I guess still beyond, but below is kind of the way I guess I would describe it. So really, if we're doing a line segment intersection test, what we're looking for is values between 0 and 1. So that being said, we know that we want a P0 and P1 value that are represented by parametric equations with scalar values, if they're on the line segments anyway, that are between 0 and 1. However, that is more or less a minor thing. If you want to do infinite lines, you're more than welcome to, and you don't have to worry about that 0 and 1 property. It's just for the sake of doing line segments, which means a specific part of a line, we're going to be doing the 0 to 1 thing. So to represent P0, we know that it is going to be basically A, the vector A, plus some scaled amount of R, which we'll represent by T. So the scalar value of R times R is going to be equal to P0. So what we're really missing here in this equation is T, which is some scalar value that should give us essentially whatever this percentage is of this length. So we don't know what that is, but that's what we're going to be trying to find out. And same kind of thing for P1. So we're going to say that that is C plus some scalar value U times S, which is going to try and give us, once again, some percentage that goes along here. And we don't know what that is either. So I think one of my blinds is going to fall down, so if something crashes, I think I'm just going to move it right now to avoid freaking myself out. But yeah, that's broken, so I'll have to fix that. Anyway, so we have P0 and we have P1. And unlike before, we can't say that P0 and P1 necessarily equal each other because they don't, right? There's a significant gap here. But what we do know, and this is why I brought this up earlier, is there's a very important property. This line created by the two is 90 degrees to both lines. So that means, or rather the direction of both lines, the direction of this green line is 90 degrees to the direction of the red line and the direction of the blue line. And so when we're talking about vectors, we know a very important definition of the dot product. Dot product is equal to the magnitude of vector A times the magnitude of vector B times cosine of theta. Theta being the representation of the angle between the two vectors. So when we're talking about two directional vectors, let's say we're going to represent, well, we know R and S represent the direction of the blue and the red line. The green line let's define as G, for now at least. G is going to be equal to P0 minus P1, and that'll give us some direction like that. We know that because it is 90 degrees to both the blue and the red line, that really regardless of what the magnitude is, because cosine of 90 degrees is equal to 0, the dot product will be equal to 0. So therefore, we can say that these two lines, these two representations of lines, so looking for I'm trying to think what the best way to do this is. Yeah, so if we have P0 and P1, so G dotted against R, we're going to have 0. And if we have G dotted against S, we're going to have 0. And so we can kind of start to expand that out a bit. And this is where things kind of start to get mathy. So if we say, well, what's the best way to do this? G. So I'm going to fill this in for both P0 and P1, which we have represented up here. So we know that that's going to be, so A plus T times the R minus C plus U times S. Okay, and then dotted with R is equal to 0, and we can kind of do the exact same thing because we know G is the same thing here, so A plus T, that's not a bracket, sorry, R minus C plus U times S dotted with s is equal to 0. And we can further expand this by filling in s and r, which would, putting those in is going to give us, well, r is b minus a, so just to avoid rewriting the whole thing, that's b minus a over there, and s is d minus c, right? So what that allows us to do then is, and I've already, as I said, kind of started to write this out, we have the same thing over here, so that's, we can kind of rearrange this, so we expand it. First, so we're getting rid of these brackets over here because these brackets really aren't worth anything. Then we're saying a minus c here, right? That's a minus c. Then t times, filling in r, once again, which is b minus a. So t times b minus a, u times d minus c, which is s, and then dotting with, and I flipped the things here, but this is d minus c and this is b minus a. So what we have here then is two equations. These are fully pulled out. I'm re-simplifying again, so I'm redefining r just in case because it's no longer written on your screen here. So we've got b minus a is r, s is equal to d minus c, q, which is a new variable here, is equal to a minus c. So we're saying q plus t times r minus u times s, dotted with s is equal to 0, q plus t times r minus u times s, dotted with r is equal to 0. So we've just written like the same thing 3 times. I'm just clarifying the steps that I'm going through to make this more simple. Then we're, expanding this thing because we've got a bracket right here. So we're expanding this out, so that becomes q dot r plus t times r dot r, right? There's an r here, so r dot r times t, and then s dot r times u is equal to 0. And kind of a very similar thing we're doing on the bottom here. And what this leaves us with is a system of equations, and this is where we can start to solve things, because we know that although we have two unknowns, aka t and u, although we have these two unknowns, they are the same in both of these equations, and therefore, because these are two separate equations, we can use them to help us solve for t and u, because the basic rule of thumb when it comes to systems of equations is that you need to have as many equations that are unique as there are unknowns, and so we have two unique equations and we have two unknowns. So most of the rest of this is just going to be me doing the stuff by hand, because that would have taken a lot of time to go through and talk about, and I don't want to make a super long video. So basically what we're doing here is we are trying to find u by itself, so we're just taking, I guess, what would it be, q dot s, so we're taking this equation here, and we are finding u. So we take all this stuff over here, we move it to the other side, which becomes negative, then we bring the negative in the s dot s and divide by it, but because there's negatives both here, they cancel out, leaving us with q dot s plus t times r dot s over s dot s for u. Of course, that has t in it, hence why this is a system of equations. So we're going to plug this u value into our other equation up here to solve for t. So to do that, that's going to be q dot r, and as I said, this is where I'm going to start actually writing stuff, times t r dot r, right? We're just copying basically that top equation. And we're filling in u here, so u is q dot s plus t r dot s, and it is divided by s dot s, and then that is multiplied by s dot r. Alright, so hopefully you can see what I've done here. I've just plugged in this u value up into this u spot here, and now we have a system with only t's in it. So although it is a bit of an algebra hoop to jump through, we can solve for t, and that's what we're going to do, because that's the only unknown, and that's really what was stopping us from finding our p0 and our p1. So to do that, we're going to first, I guess, expand this out, so multiply that out, so that's going to be q dot r plus t r dot r minus, and we'll keep the minus there, that's going to be q dot s, and we'll multiply this out, q dot s times s dot r plus t r dot s times s dot r. And now we should also take note that the dot product is commutative, so r.s and s.r are actually the same thing, and that'll also come into play when we're writing this out in code form, because there's no point in defining both r.s and s.r doing two different dot products if they're equal to the same thing. That's like doing 2 plus 4 and 4 plus 2. Like, it doesn't make any sense, right? So we will talk about that when we get to the code, but that's really a minor thing. So yeah, that's where it leaves us. Sorry, and I guess I should have been careful to write that these are both equal to 0, and that is very important. So our next step here, I think we are going to multiply both sides by s.s just to get rid of that denominator part, and hopefully that'll simplify some stuff for us. So that's going to be q.r times s.s plus t r.r times s.s minus q.s times s.r. This stuff's just the same as what was on the numerator because this just got canceled out there. So plus t r.s, or sorry, I guess I'm also doing the multiplication by -1 here because I'm getting rid of these brackets now, so we're also multiplying this by this negative symbol here, so that's negative q.s times s.q minus t r.s times s.r, and I'm kind of running out of space here, so hopefully I can squeeze that in, and I just managed to. So now we're really just solving for t here, so we're going to keep the two t parts, which are this and this, on the left hand side, and we're going to move the other stuff to the other side. So let's give us a little more space, so that's going to be t r.r over here times s.s minus t r.s multiplied by s.r, right? And that is equal to, because as I said, we're moving these other parts to the other side now, so that is going to be equal to negative q.r, sorry, bracket there, q.r times s.s there, and now because this was negative here, this is now becoming a plus, so plus q.s times s.r. Right. Okay, and then we're going to factor out the t, so to do that, that becomes t times r, factoring it out, t r.r times s.s minus r.s times s.r, which once again, I can't stress this enough, are the same thing, is equal to the same thing on this side. So I'm just to save us a little bit of time, I'm just going to draw an arrow there because it's we haven't changed anything on the right hand side. We're just or actually, one thing we can change on the right hand side, just to make this a little nicer looking, we'll flip these around. So it's going to be q.s times s.r minus q.r times s.s. Right, so all we did was we just switched places of these two things so that the positive was in the front. So finally then, that means we can solve, I think, for t now. Yeah, we can. So t is equal to, this stuff is the same, so this is going to be q.s, and I'll try and make this a little neat because this is what we're going to be copying the equation from later, so that's going to be, I just can't seem to draw a bracket, q.s multiplied by s.r. Right, we're just copying the top right now, or the numerator, q.r multiplied by s.s. and then that is all divisible by the denominator, which was the part that we factored out, so that is r dot r multiplied by s dot s minus r dot s times s dot r. And that is it. That is t. We have found t. So this is what t is equal to. And to find u, we would calculate t and plug it back up into this guy. So that's really all we need. We have our u and our t. So to find p0 and p1, we would just plug those in. So that becomes a plus t times r. And p1 becomes c plus u times s. And now, as I mentioned earlier, if the two lines are technically intersecting, and we'll talk maybe a little bit about margin of error once we get into the code, but if those two lines are intersecting, then p0 and p1, p0 minus p1 here, should have a magnitude equal to 0. So that is what we need to do. So let's actually hop into the code. I know that was a lot of math stuff, but let's hop into the code and actually try it out and see what happens. So I will see you guys there. Okay, so let's take a look at the code. So this is the function that does the calculation of the intersection. So in terms of input, we have 3 or 4 points, so A, B, C, and D, right? Those are just the points that build up our parametric equation. Pretty straightforward. We have 2 output vectors, which are P0 and P1. Those are the 2 calculations. We have an output bool, which is telling us if the I actually can't even remember. So if the P0 and the P1, regardless of actually if they're intersecting, if P0 and P1 are actually on the line segment, and if the output bool intersects. So there's an output bool that tells us if the 2 lines do in fact intersect. So I've also written here a public float, which is a margin of error. And all this is a margin of error because computers tend to lose maybe a couple, if it's a really precise equation, which this is, computers tend to lose maybe a couple decimals that are really far in. So like we're talking like thousandths. It depends really, depending on the the type of I'm trying to think of the word, the type of value that you're using. So floating point is usually pretty good, but if you want to be more precise, you can use something that holds larger numbers and is more precise. And you might not necessarily have the option to do that. That's very dependent on the language that you use and so forth. So the margin of error is really important in that case, because if you're losing that preciseness of your numbers and your t and your u values, then your p and your p0 and your p1 may not get a specific perfect value, and therefore when you do the subtraction here, aka the subtraction here, the magnitude subtraction, then they may not be equal to 0. That might be like a 0.0001 difference, which is not 0, and it might not be noticeable to the human eye, but it pretty much intersects, right? So that's what the margin of error is here. It just allows us to be a little less precise, but as you can see, it still needs to be at least 0.001 magnitude units close to itself, or the 2 lines need to be within that magnitude of intersection, I guess. Anyway, so looking back at our equation, I know that was maybe a little beefy there. Looking at our equation, and I'm trying to figure out the best way to get this on the screen. Right, so our t value here, we're calculating a whole bunch of dots. So q dot s is right here. We've calculated that there. Q dot r here, we've calculated it up there. R dot s is here, and recall s dot r and r dot s are the same thing. So, and that's the same for s dot r. So there we are. R dot r. So these things are all covered. R dot r is here, and s dot s is here. So we've got all the things covered there with our dot products. We did the r, s, and q, which, as we talked about earlier, up here is our simplification to make things easier for us. Then we're doing the denominator, so the denominator is r dot r times dot s minus dot r dot s right here times s dot r Then for the numerator, we've got dot q dot s, which is the top, times s dot r, or r dot s, right? Same thing, minus q dot r, r dot q, q dot r, same thing, times s dot s. So then we just solve for t by taking the numerator divided by the denominator. We plug it into u to get u, right? So dot q dot s plus t times r dot s divided by s dot s. That gets us u. And we plug it in down here for our p0 and our p1. So, oops, didn't need to add a space there. The last kind of step here is for on segment, we're checking basically, we automatically set these to false. So, as I mentioned way earlier, right at the beginning, if our values lie between 0 and 1, we know that they're actually on the segment, and that has to be true for both of them. So if t and u lie between 0 and 1, then we know that the 2 points P0 and P1 are actually on both segments, and as I said here, if we do the P0 minus P1 magnitude check and it's within the margin of error, we will say that the two lines do in fact intersect. So in terms of actually putting this into play, I just had a few points A, B, and C, which we saw are easily maneuverable. I got the P0, the P1, some bools, stuff like that, booleans. We're doing the calculation of the intersection. We're drawing the line. If the two lines, like if the u and the t values are on segment, then we are in fact going to draw a green line between them, and we'll finally just uncomment this last little area, which is going to print for us if we are in fact intersecting or not. So let's hop into Unity and actually check this out. So we can see in the bottom here if it's on segment and it's intersecting. So right now, these two lines are definitely intersecting. So if I move these though, it's going to tell me, oops, I'm moving the wrong thing. If I move one of these, it doesn't matter which, we can see that we no longer intersect, but we are still on the segment because the two lines connected by this green line are in fact on the segment. So if I move these in a position where that green line is not on the segment, there you go, for example, then we get false and false. So yeah. So we could change the margin of error if we wanted to, so we can use like 1 unit. That's very large. It's not going to at all look like the two things are intersecting, but it will work for us. So technically, because there's that margin of error of 1, it thinks that this is intersecting. So we could adjust that value if we wanted to, and as you can see, once we kind of move out of that 1 unit range, that green line becomes longer than 1 unit of magnitude. It no longer thinks the things are intersecting. So that's pretty much all there is to it. You can do some pretty neat stuff with this. Maybe, I don't know, you want like intersecting lasers or something like that. I don't know. It's your game. But I thought this was an interesting thing to make a video on. So hope you guys enjoyed and hope you learned something new. I will include the source code, at least for the actual calculation here. I'm not sure what I'm going to do about the vector3 because that is a Unity class, so maybe I'll write a vector3 class that can do some very basic operations, but we'll see about that. I don't know. I think hopefully most people are familiar with what vector3 is. Anyway, so thanks for watching and see ya.